We have people coming into the room. I'm Will Harris. I'm Vice President of EnviroPod here in California. Welcome to the webinar that we are beginning here shortly. And let me make sure my phone is turned off so we're not disturbed with phone calls at this time. And we're going to wait a couple of minutes here for others to join our presentation today on standardizing trash capture for a resilient stormwater infrastructure. I want to welcome you all, and we have attendees from almost all over the world, a lot from the Western Hemisphere and from down under, New Zealand, Australia. I believe we have one or two attendees that are joining us from Europe, specifically around Germany and England. Thank you very much for joining us here. I'm on California time, where we are commencing this webinar at 1 o'clock. I will begin this in just a moment or so, but I just want to let you all, we are having a poll taken. Just a couple of simple questions we'd like you to consider answering about your position and where you're all from. And also during the actual presentation halfway through, we'll be sending out another question as well. So feel free to fill out the information that best describes where your position in the stormwater industry. We'd love to know who is joining us, not only for this webinar, but for future webinars that we intend to do. And then go ahead and submit that information as well. So again, thank you all for joining us. My name is Will Harris again with EnviroPod. I'm Vice President of EnviroPod USA. We're based in California, and I will be introducing our speakers here as we go through the introductory period and guidelines for the webinar, which I'll commence in just a moment here as well. So we also believe that your speaker should be turned off, but you do have the ability to ask questions at the top of the screen. You should be able to see a question or Q&A where you can ask questions there. You can also leave comments through the presentation. We will be answering questions at the end of the panel discussions at hopefully close to a quarter before the hour is over. This presentation will be running approximately 1 hour, and depending on how many questions we receive, we may go longer than that, but we're hoping that you all be participating, and we would love to have you make comments or else provide questions so that our panel can be able to answer those questions. So I'll go ahead and begin with the agenda for this webinar. We'll talk about a little bit about the webinar guidelines. I think I pretty much already explained them to you. Overview on why we're here. And then we'll go into a presentation, which will be done by our first speaker, Julia Watson, the hydraulics of flow-through screens and catch basin inserts, our CBIs. And then our panel will join us with Mike Hanna and Jim Lenhart. I'll be introducing them after Julia's presentation, and then from there we'll go into the questions and answers as well. So I would be remiss if I didn't explain who we are at EnviroPod. This is the only commercial segment of this webinar to explain to you who we are, for those of you who don't know EnviroPod, and also where we're located. EnviroPod Incorporated is based in California, but we have distribution centers throughout the USA and Canada. We're part of a larger group called the Stormwater 360 Group, which is actually based out of Auckland, New Zealand. We have manufacturing facilities worldwide, including Mexico. Our focus is not just on developing and providing stormwater treatment technologies. That's our bread and butter major focus, but we are leaders, and we continue to focus on how to make the technologies even better through our research and development group, which Julia Watson is the lead on that, who's going to be joining us today. We have well over 30 years experience in California as well as in the USA, in stormwater expertise. But the good news with our products, we can deliver our products to our customers in 7 to 14 days on average, anywhere across the United States. And we have a very, very large warehouse located in Oceanside, California. For those who don't know Oceanside, it's not too far away from San Diego, where we keep a full stock of our products at that location. And with that, I will just introduce the LidaTrap, which is the product that we have developed over the past 27 years at EnviroPod, and Stormwater 360 is a small catch basin insertable device that is easily retrofitted inside of catch basin inlets of any type. There are now over 65,000 LidaTraps installed worldwide. And since 2000, we have over 5,000 LidaTraps installed in California. So that gives you an idea about why we're here and our hosts. One last point to make on that is that the LidaTrap is certified in the state of California as a certified full trash capture device. And this is a copy of the actual certification that manufacturers must show or must obtain from the California State Water Resources Board. So with that in mind, I can now drop out of the commercial segment of this and talk about why we're here and why you're all interested in joining us. And thank you again for joining us from across the country, especially from California. We're going to do a little bit of trash talk here about the regulations in California and what makes California different than maybe the rest of the country or the world for that matter, and also the definition of trash as it's defined in California may not be defined the same way in other states or other parts of the world, but we need to define that of what we're actually designing the systems or any device for that matter to capture trash. Also an example of why we're really here, and that is to show examples of what a trash looks like at the end of the pipe. Well, I know a lot of folks see or hear about the Pacific garbage patch, but you're going to see a little bit example of that shortly. And also to really go back to the source of how we are implementing trash capture, or how the state of California as well as other states are implementing ways of capturing trash through practices or treatment systems. We're going to talk about small at source best management practices, or catch basin insert filters in particular, and then really discuss the problem and the challenges around implementing those trash capture devices inside of those catch basins and what impacts they may have on the hydraulics as well. A little bit about this is my trash talk portion and why we're talking about trash in California. California is unique. It defines trash as any particle size that's 5 millimeter or larger. As I mentioned earlier, that may not be the case for other states or locations who don't have an exact definition of trash, but any device that is manufactured or made or a practice must mitigate particle sizes that are 5 millimeter or larger in size. That's an actual legal definition in California. And with that, it has to be designed and built around meeting the standards that California has enacted around capturing the first design flush flow. In California, the design flow is capturing any flow rates of a 1 year, 1 hour storm. And then the device has to have the ability to bypass peak flows or larger flows that go beyond that. We'll get into a little more detail on the studies we have found of the hydraulic conditions within these catch basins and go from there. Here's what we're looking at in terms of what we're trying to prevent or stop from happening, and that's going on not only in the Pacific Ocean, but around the world. You're getting a peak view of the Great Pacific Ocean garbage patch, where marine debris, primarily plastics, accumulate due to ocean currents located between, and this is between Hawaii and California, where the Pacific garbage patch is located. Now, there's garbage patches and currents around the world now that we're seeing this type of problem that's going on. But once it's in what I call the big drain, the big sink, if you will, it's very difficult to get out. And the whole purpose of developing these requirements and regulations is to prevent this from happening, because the cost of trying to remove it here is still in the theoretical stages, but almost impractical overall. I won't get into that from any standpoint at this point, because that's not why we're here. We're really here to address it closer at the source, which is really here in terms of where trash accumulates and collects inside of catch basin structures of all sorts and different sizes and shapes, and can convey this material out to the ocean. Catch basins were originally designed, as you know, to be able to convey water off of a roadway or a parking lot or a site to prevent flooding conditions. And that's why good engineers have designed catch basins for the past couple of centuries. But it also conveys everything else that goes with it. So the purpose of developing and designing insert devices is to be able to capture that trash and debris at the catch basin or at the source, and to make it effective enough to capture 100% of all that trash and debris. But it also raises questions on the ability for a technology or a provider of technology to be able to design the system without impacting or affecting what the catch basin was originally designed to be, which was to move water off the site. So with that in mind, we're going to discuss what the problem really is. And with that, if I can go ahead and move my questions here for a sec, is really not just about building technologies, but it's about retrofitting existing catch basins and how they affect the existing systems of driving water through there, and as well as do these catch basin inserts, do they have the ability to really be maintained properly, and how should they be maintained, and how often should you maintain them? So this is all described in the problem that we have been able to identify and be able to describe in modeling different hydraulics of a catch basin. And in California, current California design standards rely on simplified calculations that can significantly overestimate catch basin insert capacity. And this webinar presents innovative research comparing 4 methods for evaluating catch basin insert hydraulic capacity, which will show not only laboratory testing, but also modeling that has been developed and shown here, which I'll introduce Julia to describe and be able to move through on this webinar. So you will see advances to the computational fluid dynamic modeling has been done, and we will then, she will then be able to provide you with further details and information on how we are addressing that problem. So I'm going to introduce our first speaker, Julia Watson. Julia, excuse me for a second here, has been with Enviropod for a number of years, and she's a very passionate and experienced R&D engineer, currently leading research initiatives at Enviropod.
Okay, it looks like we may have lost Will, so I will just continue with the presentation. So thank you, Will, for the great introduction. As mentioned in the problem statement that Will was outlining, these trash screening devices are typically online, which requires them to convey peak flows. And so therefore, our study began by examining the capacity of screens used in the devices themselves, which forms part 1 of the study. And if you were present at my CASCA presentation, you will have seen these slides before, so please bear with me, because from there, we have moved on to assess the bypass capacity of these screening devices and how the bypass flow interacts with the catch basin. And that makes up part 2 of the study. So we'll start by looking at our lab testing setup, including how the test differed depending on the type of device. Then I'll walk you through the 4 methods that we use to estimate the maximum capacity of the test screen and how we applied those to a theoretical basket. And then finally, we'll shift into part 2, where we use computational fluid dynamics to explore a full-scale example. So the first set of tests that we did aimed to replicate the conditions of a basket suspended in a catch basin. So as shown by the blue arrows in the image, the basket operates under free discharge conditions, meaning the outflow from the discharge is unobstructed and the flow discharges directly into the air. So in this setup, there is no back pressure or downstream resistance, and the water simply exits the device and is allowed to flow freely. And here is how we recreated these free discharge conditions in our lab. So the schematic shows our lab testing setup, which I'll briefly talk through. We used a recirculating water system. We were pumping water up from a tank up into a flume. And for this test, the screen was positioned at the end of the flume, allowing the water to freely discharge into our mock catch basin before flowing back into the tank. You can see this setup in the photo on the right. So during this testing, what we measured was the water surface elevation behind the screen, and we did this across a range of flows to allow us to build a complete data set for our analysis. The second round of testing was designed to simulate connector pipe screen conditions. These devices are typically installed at the bottom of the catch basin or within the sump. As indicated by the white arrow and the water level behind the screen in the image, CPS or connector pipe screens operate under tailwater conditions. And so in this scenario, the water does not discharge freely. Instead, the flow passing through the screen is resisted by the depth of the water on the other side of the screen, which is at the outlet pipe. And then this is what we refer to as tailwater. So it creates a different flow dynamic when compared to the free discharge case that we've already looked at. To reflect tailwater conditions in our lab, we made the same adjustments, some slight adjustments, but we had the overall setup the same. So in this case, we positioned the test screen mid-flume. And so this allowed water to build up both upstream and downstream of the screen, simulating the tailwater environment we saw in the previous diagram. So during testing, we measured the water surface elevation on both sides of the screen. And this let us calculate the difference in head across the screen, which was critical for understanding how the tailwater impacts the screen's performance. Here is an overview of the 4 methods that we used to determine and compare the capacity of the screen we tested in our lab. I will go through each of these individually now. Method 1. This is the orifice equation approach. And so this method uses the single orifice equation, and based on a review of the publicly available California Water Board certifications for trash fall capture devices, this is the most commonly used design approach. In the context of a basket, this method treats each side of the basket as if it contains a single orifice, as shown in the illustration. Knowing that actual screens have multiple openings, this is clearly a simplified representation. Take note of the quote at the bottom of the screen. In its original context, it's essentially stating that if you're going to use such a simplified flow calculation method, empirical testing is necessary to determine an appropriate discharge coefficient for the screen, which is exactly what we were doing in our lab. Our empirically derived coefficient for the screen was 0.41. For comparison, we also calculated the screen's capacity using the commonly assumed value of 0.61, which is an appropriate value for a single sharp-edged orifice. The second method we considered still uses the orifice equation, but instead of simplifying the screen to one orifice per side, it analyzes each individual orifice and row, as well as the driving head for each row. So we developed this numerical model, which is illustrated on the right, to gain a more realistic representation of the screen's capacity without needing empirical testing. And so this makes it a more detailed and less simplified approach than method 1. On this occasion, because the model is considering each individual orifice, which does have a sharp edge, we have used the standard discharge coefficient of 0.61. The third method relies on a stage discharge relationship. Using this approach, we calculated a specific flow rate. And so that is the flow per unit area of the screen. And we did this for various water surface elevations. So this allowed us to apply the results to different screen geometries, and it effectively combines the multiple driving head that we saw in the previous method, as well as our empirical testing of the screen. Finally, in our fourth method, we used computational fluid dynamics to model the lab setup. Once we were confident that our model was accurately reflecting our real-world conditions, and specifically was matching the observed water surface elevations behind the screens, we trusted that the parameters within the model were correct. We then went on to use the CFD model to simulate a basket configuration and compared that to the calculations from the other three methods. Okay, so what were our results like? Well, what we did first was we used each method to determine the maximum flow rate that could be passed through the screen that we tested in the lab. And a schematic of that screen is shown on the left. For the single orifice method, we calculated the maximum flow using both the assumed discharge coefficient and the one we measured that was specific for our screen material in these conditions. And as you can see from the left bars on the graph, the measured coefficient results closely match those of the other three methods. And in comparison, the assumed coefficient overestimates the capacity of our screen by about 1 CFS. And so therefore, we ignored the far left result and concluded that the maximum amount of flow that could be passed through our screen is 1.9 CFS. Next, we applied each of those methods to a basket design, and that was just a theoretical design for a 24-inch by 24-inch catch basin. And the basket dimensions are shown on the left. Again, the graph shows the results, and on the left side of the graph, we see that the single orifice method has overestimated the basket's capacity, and that's even true when we have used our coefficient that were determined in the lab. In contrast, on the right-hand side of the graph, the other three methods show fairly good agreement. And of those, the stage discharge method estimates slightly higher flows than both the CFD model and the integrated orifice approach. Next, we used each method to calculate the change in water surface elevation, or delta H, that we would get across the screen for the maximum flow rate of 1.9 CFS. In this graph, the delta H is shown on the y-axis, and a smaller delta H indicates a more efficient screen. So the single orifice method suggests the screen is too efficient when we're using the assumed coefficient, but also overly restrictive or too conservative when we're using the coefficient we measured in our lab conditions. The remaining methods, again, though, show fairly good agreement overall, and the CFD methods align particularly well with the stage discharge. So in summary for part one, we found that using a generic discharge coefficient of 0.61 with the single orifice equation alone can overestimate the flow of a catch basin insert by up to 250% for the basket that we looked at. And while simplified methods are useful, greater accuracy does come from using empirically derived values, which is something that we've taken steps to standardize with ASTM. Tailwater was also found to be a key factor in the screen efficiency. I think the images on the right show this quite clearly. So in the top under free discharge conditions, the velocities at the bottom of the screen are much higher, which is indicated by the intensity of the red. With tailwater, the image below, the flow is more subdued and it affects the overall efficiency of that screen. Now, we'll move into part 2 of the study, and we'll shift our focus to bypass capacities and how these devices interact with the catch basin itself. So we begin by evaluating bypass flow using 2 methods, and that was the single orifice method, which is typically accepted for bypass analysis, and a more detailed CFD-based approach, which allows us to better visualize and understand the flows. This part of the study was to help us understand not just the device performance in isolation, but how they behave within the full drainage system. As I just touched upon, because the bypass is typically a single opening, it makes sense to use the orifice equation for this part of the analysis. On the left, you can see the bypass openings at the top of the basket, with the flow path indicated in orange. For the CPS screen on the right, the bypass is also located at the top of the screen, and again, I've indicated the flow path in orange. It may be a little bit hard to visualize from these schematics, but I've got some more diagrams as we go through and dive into the details. What you're seeing here is a CFD-generated model of a 36 by 36 inch catch basin with 2 baskets set within it. The red line indicates the point where surface flooding begins, and we have multiple different flow rates across the screen. Our hand calculations estimated that a bypass capacity for this configuration of the 2 baskets would be 9 CFS. However, the CFD simulation shows that flooding is beginning to occur at just 5.3 CFS. So one key observation from this work was we noticed some air pockets, which are highlighted with the red circles on the 3.5 CFS image there. And those air pockets appear to be significantly reducing the bypass capacity. And so this is a great example of how the geometry and interactions with surroundings can affect the performance, which is something to keep in mind as we move forward and look at some more examples. To help guide our full-scale CFD model, which is of a 7-foot curb inlet catch basin, we began with a literature review focused on curb inlet basin design. We also drew on data from the LA County technical report on connector pipe screens, which is shown here, and that helps us shape some of the parameters for our model, which I'll go into more detail on the next slide. From the literature review, we found that curb inlets are typically designed with the hydraulic grade line below road surface and usually comprise a comfortable freeboard of about 1/2 to 1 foot, both parameters I have highlighted in the diagram in blue on the left. So these images here are taken directly from the LA County technical report that I showed you on the previous slide, and they represent the setup we replicated in our CFD model. What you're seeing are the dimensions of the connector pipe screen that we placed inside the 7-foot catch basin. The screen height is 18 inches, and above that it is a 6-inch bypass, and the screen radius is approximately 11 inches. The overall depth of our catch basin, including the curb height of 8 inches, was 3.5 foot. And so this setup gave us a realistic foundation for analysing how the system performs under real-world flow conditions. Here is an example of our CFD model in action. So in this case, the model is empty, meaning there's no screen or no insert present. We've simulated flooding this catch basin to determine its maximum flow capacity under ideal conditions, so no tailwater or catch basin insert. From this setup, we've found that the catch basin can receive and convey up to 12.4 CFS without flooding. And so this gives us a useful baseline to compare against once we put the different screening devices into our model. In this scenario, we have placed our CPS into the catch basin, and we have blocked 100% of that screen. So all of the flow, which in this case is 5.3 CFS, is being forced through the 6-inch bypass of the CPS alone. From the video, you can see the system reaches a state of equilibrium with the bypass handling the full 5.3 CFS without surface flooding. But just like in the basket example, that's slightly lower than what our hand calculations predicted, which was just over 6.1 CFS. Also notice that when we compare this to the empty catch basin that I showed you on the previous slide that could handle 12.4 CFS, the catch basin has now been becoming quite full at just 5.3 CFS, which is less than half the maximum flow that that catch basin is capable of. So while the system is functioning, it's just another good example of how the geometry can impact the performance of these devices, especially when we're using simplified flow calculation methods. On the next slide, I will explain a little bit more about why. This here is the cross-sectional view of the CFD model that we just looked at. So take a look at the white region that I've highlighted there. That's trapped air inside the system behind the connective pipe screen. The air pocket has formed due to the way in which the flow through the bypass slot is interacting with the geometry of the screen and catch basin. That air pocket is restricting the flow, which helps explain why the bypass capacity ended up being lower than our hand calculations suggested. It's also important to point out the limited freeboard again in this case. The total depth of the system is 3.5 foot, including the curb, yet the water level reaches 2.7 feet within the catch basin, leaving just 10 inches of freeboard. And again, just to emphasize that this is occurring at a flow rate well below what the catch basin is theoretically capable of handling. So I thought I'd ask the audience here, if Nicola can get the poll to go, if anybody could think of a way that we might be able to get rid of this air pocket problem, like what kind of solutions could we use to prevent this from happening? Okay, I think there might be a slight problem there, so that's okay. But what we'll do now, okay, we've got that. Cool, so any ways you can think of that we might be able to get rid of having this air pocket problem within the catch basin when using a catch basin insert. Venting, that's a good one. Give it another moment in case anybody's got anything else to say. Splitter. Oh yeah, catch basin, relief vent, lovely. Bigger insert, yes, definitely. Vortex fins. Yeah, cool, there's lots of options, isn't there? Different design, wholeheartedly agree. Snorkel, that's cool. Yeah. Multiple baskets, also a good idea. All right. Thanks, Nicola. I think we will continue now. Great opening. Cool. Great suggestions, team. Longer wear, yeah. Perfect. So you're right, some people touched upon it. One way in which we could minimise the impact on the catch basin's capacity is to use a trough conveyance system and avoid putting a screen at the outlet pipe. So the video here is looking at within a curb inlet catch basin and is an example of our trough system, which was designed to allow easy maintenance of the basket via the manhole in the sidewalk there. But how is this so different to the CPS though? Well, in the CPS example we've been looking at, the flow is required to go through the restrictive 6-inch slot of that 11-inch radius. And so when we're assuming that the screen is completely blocked, the bypass is effectively becoming the outlet pipe. Whereas in the trough example, the bypass is not so restricted. It's allowing flow to freely discharge over the length of the 7-foot weir, and the outlet pipe is also not obstructed. So therefore, the trough arrangement is able to better preserve the hydraulic capacity of the catch basin itself. Here we have velocity animations of our CFD models. And again, we have the connector pipe screen in the video on the left, and we have a direct comparison with the trough system in the video on the right. And these are both under that same flow condition of the 5.3 CFS. Just notice the water surface level differences between them, and also notice the differences in the flow at the outlet pipe. Now we'll take a look in more detail at those cross-sectional views. This slide is comparing the cross-section of the models we've just looked at, and again we have the same flow conditions. As I've already shown you, we have the tailwater and air pockets acting as a flow restrictor on the CPS, and that reduces the performance of the bypass on the left. In contrast, the Emma trough system on the right has no obstructions, and that's because all the components are suspended and water discharges freely. There's no tailwater and there's no trapped air. And so this allows the water level within the catch basin to be much lower, and that's providing a lot more redundancy in the system for larger events. This side-by-side comparison highlights our system design choices, such as using a trough or alternative design in place of a CPS, can significantly reduce the hydraulic losses and maximise the catch basin's capacity. To wrap up this comparison, we are now looking at the trough system versus an empty catch basin. And these are now both handling the 12.4 CFS. So despite having a catch basin insert installed, we are almost matching the capacity of the catch basin on the right. So the key takeaway here is that with the right design, we can retain full capacity of the catch basin while still providing effective treatment and trash capture. And in conclusion, to wrap up this study. So firstly, the single orifice method, while commonly used, probably is too simplistic for calculating screen capacity because it can overestimate the performance, particularly for a more complex geometry. And so to validate the use of such simple flow calculation methods, we must physically test the screens to define appropriate parameters for our calculations. The orifice method can still be appropriate for estimating bypass flow, but even then we saw that the results are highly sensitive to the geometry and the device layout, especially when we have unexpected interactions resulting in things like air pockets affecting the performance. A key limitation across all standard methods is that none of them account for how the devices interact with the catch basin. And as we've seen in the CFD simulations, those interactions can dramatically influence flow behaviour and the capacity. Looking forward, there is a growing need for standardization, not only in these devices and how these devices are sized and specified, but in how they are evaluated within full system context. So this is critical to ensuring we're building resilient, future-ready drainage systems. And that brings us to today's reality. With California recently facing multiple atmospheric rivers and significant urban flooding, this kind of work isn't just academic, it's actually a real-world issue. So as storms become more intense and less predictable, understanding how these devices perform under stress is more important than ever. And with that, I will hand back to Will, who will introduce Mike and James for our panel Q&A.
Thank you, Julia. I do apologize because I either got the hook or I dropped out of the meeting there for a second from a poor internet connection. Just want everybody to know, Julia did not give me the hook. It happened accidentally, but I apologize because I didn't get a chance to really give a thorough background of your background, which you've done quite well just by this wonderful, excellent presentation. So with that in mind, I am going to introduce our panel now, and this will open up for questions from attendees who are here in the webinar as well. First, Julia's on the panel, but I want to introduce Mike Hanna. Mike Hanna is Managing and Technical Director of Stormwater 360 and also serves as Technical Director of Enviropod International. And with more than 30 years experience in the industry, Mike is widely recognized for his leadership in stormwater technology development. I'm getting some feedback here. That's somebody else? Okay, thank you. Regulatory engagement and product performance validation. Mike is also co-author of research featured in this webinar and played a key role in sponsoring and guiding this project on this study. Mike is the inventor behind globally adopted products such as the LittaTrap and EnviroBasin. There are now more than 60,000 LittaTrap installations worldwide. He's also presented technical papers and spoken at numerous North American conferences, including StormCon, CASQA, APWA, and is contributing to leading the industry in forums in Europe, Asia, and Australia. Welcome to the forum, Mike. I'm also going to introduce Jim Lenhart. Jim, I think you're in the audience somewhere. I can't quite see you out there, but I think you're there. Jim is the owner of Stormwater Northwest. He is former Chief Technology Officer of Contact Engineered Solutions and was the technical founder of Stormwater Management Incorporated, which developed the Storm Filter. I think a lot of people though might recognize the Storm Filter. Jim is named inventor of multiple U.S. patents in the field of stormwater treatment. He has authored over 60 papers about water quality and stormwater treatment, mostly from results applied to research and stormwater monitoring programs. He also has served as an instructor of civil engineering at Portland State University, where he's taught hydraulics and water resource engineering. He's also an active member of the Water Environment Federation, Stormwater Policy Committee. Those of you might be familiar with ASTM E64 on stormwater control measures. Jim holds a BS in Plant Services from the University of Arizona and a BS in Agricultural Engineering, MS in Water Resource Engineering from Oregon State University, and is a professional agricultural and environmental engineer. I didn't know you had that part of your position, Jim, with over 30 years experience and is a diplomat of the American Academy of Water Resource Engineers. So welcome to Jim. Thank you very much. Let's go ahead and open up the panels to questions and answers. And of course, Julia or Mike or Jim, you're welcome to make some comments now after the fine presentation by Julia, and I'll let it go at that. Mike or Jim, you'd like to add to this at all?
I'd just like to say, well done, Julia.
Thank you very much. Appreciate it.
And I think the work highlights some of the risks we have when we implement new solutions. You know, we're trying to solve one problem here, we're stopping trash, but if we don't think about it hard enough, we might be creating another problem somewhere else. And humans tend to do this with their enthusiasm sometimes. So I think that's a great presentation, and you highlighted some of the risks that is really a driver for why we need to standardize the approach with trash capture devices.
We do have a comment and questions from Daniel, and please help me if I'm mispronouncing the last name. Career. It's Kehrer. I apologize if I am not pronouncing that properly. But the comment from Daniel is, this is a great analysis for clean, clear screens. Over time, the screen itself will lose capacity. Have you evaluated flow rates with 10%, 25%, 50% blockage? Or does the bypass maintain the capacity regardless? Just treats less debris when full. Any comments from the panel?
Yeah, I've potentially wasn't as clear as I could have been during my presentation on that. So when we modelled the basket, or applied our calculations of the screen capacity to the 24-inch by 24-inch catch basin insert basket, that was assumed half the screen blocked on all of the catch basin insert. And similarly, when we were looking at the bypass capacities, all of the screens are assumed to be blocked because worst case, they're completely plugged up with plastics and no flow can get through there. But then we have assumed that the bypass would still be available for flow to go through. Did you have anything to add to that, Michael, Jim?
Yeah. Look, the Californian Water Board, Enviropod designs states all our flow rates based on the screen being half occluded, the bottom half, or it being half full of trash and debris. The water board applications, a lot of them have different. This is another example of why there needs to be a standard approach. Some people are claiming empty baskets. Some people are claiming 3/4 full baskets. So we need to standardise, or how are we assessing or calculating flow? It should be a half full basket or a 3/4 full basket or whatever it happens to be. So at least when the purchaser or the acquirer of these technologies, they understand what the assumptions are around that flow rate.
I think also would mention that ASTM E64 has developed a standard for testing trash devices. And part of that protocol or procedure is to incrementally block off the screen and develop a stage discharge curve, if you will, as a function of percent blockage.
But I think the other point that we didn't consider blockage of the bypass. That was assuming no blockage. And obviously when a big storm event's happening, and you have a lot of gross pollutants coming in because of the intensity, these bypass structures can get blocked up, and maybe again some sort of safety factor really needs to be applied on bypass flows as well for that occlusion.
There's a subsequent question or comment also from Daniel from the previous question, as he's asked to confirm these screens are size 4 or 5 millimeter size, aperture size, plus or minus 1/5 of an inch. Is trash capture consistent with California Water Board requirements correct? I think that's the way it posed the question. Other states may have a less restrictive size of acceptable debris. Any comments on that?
I think
I would say that the 5 millimeters become somewhat of a quasi-standard globally for a gross solid. It is the sizing down under. We've always said, and it's 5 millimeters or larger. So there is no, with California, there is no variance allowed. You pretty much have to capture 5 millimeters, because 5 millimeters or larger, because it's written into the legislation as that. So.
And I think ASTM also defines trash and debris as 5 millimeters or greater. Basically, that was adopted from California.
So in terms of a general question having to do with the maintenance of these devices, of any insertable device, what's the panel's thoughts on recommendations for maintenance of connector pipe screens versus baskets versus other technologies out there? Does these results of the modeling and analysis conclude that owners or end users need to go out and maintain connector screens or catch basins that have connector screens more often compared to other type systems, or is it just basically all the same?
I'll go for it. I like to be a bit of a pragmatist, really. The reality is these devices are often not maintained, and the load is really highly variable. Outside a sports stadium, you can have massive trash loading, where in a residential subdivision there may only be a few leaves or something like that. Often things like cars parked on top of devices and things like that cause issues with maintenance requirements. So regardless of how often these systems need to be maintained, the bypass capacity is essential. Because they may not be maintained. The other thing is too that if in a situation where there is a flood event and they haven't been maintained, I think these systems need to be easily cleared as well. In order to prevent flooding as well. So the trash capture and the maintenance are around about the water quality benefits, but from a pragmatic kind of flooding issues, I think it's more focused on what happens if it isn't maintained. That's my comment on that, really.
Great. Thank you, Mike. Do we have any other questions from the audience here? I think, yeah, just something just came in here. Let's see, thanks for general confirmation regarding. How often should, the question is from Heidi. Thank you, Heidi. How often should they be cleaned? I think you're in reference to, general speaking, how often should any catch basin insertable device, whether it's a connector pipe screen or a basket, should be maintained? Anybody want to, or be cleaned is the question. Anybody want to take that question on?
Well, I did a study many years ago for Snohomish County. We're actually looking at once you clean this stuff out, what do you do with it? Is it hazardous, not hazardous? But based on some of the observations we did, it tends to be, and I got chided for it. I said these catch basins tend to have a personality. I mean, some clog up and get a lot more trash and debris in them than others. As Mike had said, it depends on land use, but also a lot of trash and debris are transported by wind and not necessarily by water. The wind blows, it saltates down the street and jumps into the system. So I think what happens, what you need to do is when you have a asset management program, you have to have some level of documentation that you develop over time to know approximately when these things require maintenance, and some more than others. So I think it really varies. I did see a long time ago there was a device that somebody was testing, and I don't know what the outcome was, but they were trying to establish when these things were full and that they had some kind of a Wi-Fi connection to notify some authority to go out and do the maintenance. But frankly, I haven't seen any result of that since I read about it when it was first deployed and tested.
But as a ballpark figure, I saw that come up in the chat. We recommend between 2 and 12 months. We've had some sites where it's a heavy loading, it's a large catchment, and they may even be less than that. But then we have other sites, even up in Canada, with large deciduous leaf drops. They're lasting a year because all the leaves compress over time as well. So it is really highly variable. I think it's about a risk profile as well. If it's a commercial area with expensive shops, I would be emptying them more frequently. If there's a sign of a big storm coming, it's you need to check them. They are these catch basin inserts in the inlet to the drainage system. I can't stress it enough. If it clogs, there's nowhere else really where the water can go, except maybe into properties. So, but as a rough rule of thumb, we say 3. At least inspect them. Every 3 months.
Having been in the California area and dealing with all the different devices that we have operating throughout the state, the average inspection, to go out and inspection, has been twice a year, once in the spring and once in the fall. You may need to maintain or service the products or the systems or devices more often than that, but at least they'd be inspected at least twice a year, once in the spring, once in the fall, and that then helps determine how often you may have to maintain them in a particular drainage area. As Mike was alluding to, every drainage area has a different pollutant load condition. So there might be some areas where you're getting a tremendous amount of leaf debris or other debris flowing into that particular catch basin. And so you have to maintain that maybe more often than you would some areas where there is very little debris and very little areas where you're catching trash and debris from that section. So it does vary drainage by drainage area quite often, and also the amount of rainfall that occurring over a particular year's time. Street sweeping certainly helps, by the way. I want to give out a little bit of credit to street sweeping applications that have been applied around the state that certainly have helped reduce the amount of load going into the catch basins, but not every city and not every municipality applies or has the ability to apply street sweeping on every street, every corner, and every area. I did want to also bring out another question we found here. Let's see. This again is from Heidi. Okay, I think I answered your question, Heidi. How to do? How often should you be inspection? Twice per year. Then we have a question from Annabelle Novak. Thank you, Annabelle Novak. What is the general ballpark pricing for a trash capture device material installation? Wondering if it's worth installing a system in a variety of inlets, or if only in areas where there is a higher volume of traffic and trash. What kinds of areas are the majority of these being installed? Residential neighborhoods versus busy cities. So that's a couple of loaded questions there. Anyone want to tackle this one?
Yeah, I can tackle that. Look, Enviropod advocates for hotspot targeting. The research we've done, we see a 100-fold difference in loading in different sites. Industrial sites, garbage storage areas are very high loading, but as I said, residential sites are sometimes low in actual trash loading. So you can actually get a lot more bang for your buck if you target basically where people or activity is. We find parks have a high loading because there's a lot of pedestrians there, waterfronts, as I said, and industrial activities. Now, in California, there is a different requirement. They have identified high priority areas that are high generating areas, and they require trash management. It doesn't have to be a structural solution. It can be a non-structural solution, but that comes with also some criteria. And they require all high priority areas, and that includes high density residential housing units, any sort of retail area, schools, in general, wherever there's a lot of activity, people activity. So that's typically how we roll it out. So if you're in a non-regulated area, really wanting to do something about your trash problem, look at targeting, outside pubs and bars and cafes and restaurants, because that's where you'll get the most cigarette butts. So.
I think also, just to mention, is most people probably know that California has a TMDL for trash and debris, which basically says 100% of all particles greater than 5 millimeters shall not be discharged to receiving waters.
I think also the question that has been raised from Annabelle is, what is the general ballpark pricing for trash capture devices? And again, I'll answer that question for you as well, and anybody else can chime in behind me. But there's really no one price that fits for a device that applies to every catch basin. Cost really highly depends on the type of structure and the size of the structure. And if it's a curb inlet, how wide is that structure? And that could range widely. And I've seen pricing not only for us, but others that are out there. Generally speaking, it could be a $500 for a small little catch basin for a price for the material without the installation, all the way up to $2,000 for very wide, large type catch basins. So it depends on the size of the catch basin and the number of catch basins. So that does come into play from a manufacturer's perspective. If you're talking about installation costs, that's also highly variable because it depends on the number of catch basins, whether or not you require traffic type of traffic controls, and if it's a prevailing wage project, non-prevailing wage project, it can vary widely. So I don't think it'd be fair to the audience or to you to give out some type of number to work with. It depends on, again, the size of the catch basins, the number of catch basins. And Mike or Jim, you're welcome to make any additional comments beyond that.
Ballpark? Well, you know, I wouldn't want to speak out of school, out of place, but for a great entry 24-inch by 24-inch, how much would that cost generally? Can you know, obviously?
Yeah, I can think for something like a great inlet. Yeah, we're talking in the $400 to $500 range, around there. So that's just for the material. For installation for our products, it takes all but about 15 minutes to a half an hour to install a lid trap in a great inlet. Again, it depends on the size. It could take longer, but we always recommend using 2 technicians to install our products. And that's pretty much average with other folks that are out there as well.
I guess the good news is it's not a lot of confined space entry. You can do everything from above ground.
Correct. That does come into play, and that's a great point, Jim. There are devices out there that do require entry to maintain them, and then there's others that don't. And we offer both types of options. But the product that you saw earlier that Julia showed you an example of, what's called the EMA, the easy maintenance manhole access curb inlet with a trough system, does not require maintenance and confined space entry for maintenance. Everything can be done at the surface. And that's a key feature if folks are looking at using systems that you don't have to climb into that require special permitting.
Likewise, if you can maintain by hand, that also can save considerable amounts of money as well.
Sure. Got a question here from Daniel Tan. Thank you, Daniel. Does Enviropod have any units in Southern California? Curious because of the fires and how that impacted the units servicing. Daniel, I can answer that question. Yes, we do. We have hundreds of units and devices installed throughout Southern California. In the LA region, where the fires just recently occurred, and the horrible mess that has gone on there and ongoing cleanup, none of the devices that are installed in that region, in those catch basins, have been impacted to our knowledge, or that there has been an issue with having to replace the devices, or the fires having an impact with filling them up. What I do know, and what we do know right now, is that the devices we have installed in areas are functioning well and doing well, and there hasn't been any major impact to our knowledge. Now, I can't speak for every single catch basin, because there's thousands of catch basins in that general area that either don't have a device in, or there's somebody else's technology in there. So I mentioned that. Any other comment from anybody on the panel on that?
Nothing from me.
Okay, and a question from Arthur Mullen. Thank you, Arthur. Could you, is it the EMA device again? Or I'm sorry, show. Oh, show the, I wasn't about to start sewing it. So we'll be happy to, yeah, actually, if you look on the meeting chat, there is the Lititrap EMA kit animation that you can review. And I don't know, Julia, do you want to go back and show it again to the audience? We still have quite a number of people here, but it's up to you.
Sure, I can do that. That's no problem. There we go. Should be on your screen now.
The optimum word here is show, not so, but show. So
there it is.
Yeah. There we go. So there's a link in the chat, as well as showing it on the screen again.
And by the way, we have our own YouTube channel, if anyone would like to view any of our animations, any of our videos, we have short video clips on all of our different products and services and systems, such as the EMMA design. If you go to Stormwater TV and just type in the word Stormwater TV on YouTube, you'll find our YouTube channel, and you'll see a list of different videos that we have on that channel, and that includes the EMMA filter. So there we go. It's a little bit herky-jerky here, but I think you can get a general idea. If you go to the YouTube channel, it's at a Stormwater TV. Again, Stormwater TV, that is the search term to use on YouTube. And you will find our YouTube channel, and you'll also then find the LittleTrap EMMA filter video as well. And we have it here in our meeting chat.
Excellent.
Let's see, we have anyone else here? I'm just looking for any other questions we have. Thank you again, Arthur, for that question. I think that's the last question, and we're over the hour. Woo, I just saw that. Well, very, very good. I do appreciate everyone joining us on our webinar today. I want to thank our panel, especially Julia, for putting on a great presentation. And for all of those of you who are still in the meeting right now, we will be sending out a notification with the webinar recording. This is being recorded. And even for those who had signed up and registered but were not able to make and attend this webinar, we will be sending out that link to the presentation as well. We thank you very much. We hope this was beneficial. If you do have any questions, here is my email address and phone number that you can reach me at. We welcome comments, and of course, we will be glad to help you with any questions you might have, or in cases where you're still developing your program around trash capture. That's one of the reasons why we're here as well. Thank you again. Any other comments? Mike, do you have any comments?
No,
Jim,
well
any
done,
last minute
Julia.
comments?
Thanks, Jim. Thanks, Will.
Thanks, team.
Okay. And from there, we'll go ahead and have a great week. Thank you very much, and happy spring. Bye now.
Bye.